Are there any questions?
Hold up. How are you gonna tell me?
I know that the force between two charges, or we'll just do magnitude force, some constant, and probably better to do the 1/4 pi epsilons of naught instead of Coulomb's constant, because we're starting in that area where we're gonna need to generalize it slightly more than what we can with just Coulomb's constant. Times Q1, Q2, over R squared. The electric field is just 1/4 pi epsilons of naught. Again, this part right here. Times Q over R squared. This should not be a shock, or at least should be somewhat familiar. We have the electric potential energy, 1/4 pi epsilons of naught. Not K. Q1, Q2 over R. And electric potential, 1/4 pi epsilons of naught, Q over R. Now, as we're looking at this, notice that the relationship, as it turns out, between the force and the potential energy is if I just take the force, multiply times the distance between the two objects, in other words, R, I get the potential energy formula. Same here, take this, multiply times the distance, a distance, and we have potential. So I'm gonna take that basic observation and generalize it. I know that the electric potential and wave the voltage is going to be equal to negative E delta, actually let's stick with PD. If the electric field is constant. So I just take the electric field, multiply times the distance. The negative sign happens because, well, if I'm going from positive to negative, let's say that I'm dealing with a capacitor. I have a capacitor here that is positively charged. I have a capacitor here that is negatively charged. If I'm going from the positive to the negative, I am losing potential. So my delta V going to the right is less than 0. My electric field goes to the right, goes from positive to negative. So if I take the distance between here and here, and I multiply times the electric field in that direction, I'm going to get a positive number. But my change in potential is negative, and so we get that minus sign right there. All right, with that little tidbit wrapped up, our questions? And with calculus, you can derive it. All right, so let me define capacitance. Now, we can run into that fun thing of there are only 100 characters we can deal with. That's uppercase, lowercase, our alphabet, Greek alphabet. This C right here stands for capacitance, not coulombs. It is defined as how much charge can I put on the plate per unit voltage. So the less voltage I need, in other words, the smaller power, the smaller battery, or smaller powered battery that I have, the more charge I can put on it, the greater the capacitance. If I have on the plates an even distribution, which is an assumption that we will make. So if I have a uniform surface charge density, that is charge, not change. Density, sigma. That's going to be equal to Q over A. So no matter where I am, it's the same. The uniform charge density allows us to do the formula for the electric field, which I'm pretty sure we did last time, that the electric field strength is equal to sigma over epsilon sub naught. Pretty sure we did that last time, okay. So from this, I know that the charge on the plate is going to be the surface charge density times the area. So I just plug that into here. Now voltage, the absolute value marks is that there's not a negative capacitance. So when you talk about the capacitance of a capacitor or of some object, it is going to be a positive number. That's the absolute value signs. And so when I use that formula over there, I'm just going to drop the negative sign. All I really care about is the magnitude. And my electric field between the two plates is sigma over epsilon sub naught. So I get sigma A over sigma over epsilon naught D. And this ends up being, well, the sigmas cancel out. And we end up with capacitance being epsilon sub naught A over D. So I got two formulas here. The question is, when can I use one or the other? This formula right here is always true for capacitor. This formula right here is true for a parallel plate capacitor. So two parallel plates, I attach it to some power supply, I build up a charge. Let's see, so that's 10 meters by 10 meters. That distance between them, 0.01 meters. And all right. Questions before we actually do a little problem here? What's this?
Battery. Capacitor.
All right. So I have a 12-volt battery hooked up to a capacitor here. I have two plates for the capacitor. One will be positively charged, one will be negatively charged. Which one will be the positive plate? Okay. And therefore the one that's negatively charged? Yep. It's a parallel plate capacitor. And so first thing I want to do is figure out what is the capacitance. Well, if it's a parallel plate capacitor, I know the capacitance. Well, I have two formulas. I have Q over delta V. And I also have epsilon sub naught A over D. Well, considering I don't know the charge, using this formula is not really gonna help me a whole lot. So we end up with 8.85 times 10 to the negative, no, not negative, times 10 to the 12th. No, it is negative. 5 times 10 to the negative 12th, it is negative 12. Times my area of 100 square meters, so this is Coulomb squared per Newton meter squared. 100 meters squared divided by 0.01 meters. So that's easy enough to do mathematically. That becomes 8.85 times 10 to the negative 8. So it's 2 questions. First question, what are the units?
Is it meters squared per Newton Coulomb squared?
Wait, say it again?
Meters squared over Newton Coulomb squared?
Not quite working out that way.
That's for something else.
Coulomb
I-
squared
I-
per Newton meter?
Pardon?
Coulomb squared per Newton meter?
Yes, there we go.
Okay, what did you say?
Coulomb squared per Newton meter, you cancel out the 2 meters from the bottom.
Alright, so that meter squared cancels out with that meter squared, left with Newton meters. What is a Newton meter anyway? Abby, you look like you want to say it.
Is it volt?
Not a volt.
Joule.
Joule, oh yes, joule. Obviously, here it not in yet. So 8.85 times 10 to the negative 8 Coulomb squared per joule. That's still a bit to write down. Surely there's a simpler way of writing a Coulomb squared per joule besides Coulomb squared per Newton meter. And there it is, 8.85 times 10 to the negative 8 farads. Named after?
Farad.
Actually, it's one of the few. Volt is named after a guy named Volta. Farad is named after someone named Faraday.
Oh,
But, you know, Faraday, that's just too much to say. Questions to hear? Let's figure out the charge on the plates. I now know what the capacitance is. I know the voltage. What is the potential drop? What is the voltage between those 2 plates? What's the magnitude of the voltage between the 2 plates? Someone just take a wild guess.
0.01.
No, that's a distance, looking for a voltage.
12,
Just a guess.
Different wild guess?
12, 12,
Give me the whole thing.
12 volts.
Yeah, 12 volts. If you will recall, the potential difference between any point in itself is 0. So if I start here and I go across here, I'm going from the negative to the positive plate, or negative to positive nodes of battery. I'm gonna gain 12 volts. I know I have to be back at 0 by the time I get back to where I started. So if I gain 12 volts going here, I have to lose 12 volts going across that. So, or if I'm going the other direction, positive 12 volts. But it is a 12 volt potential difference between the two plates. And so I take my 8.85 times 10 to the negative 8 farads and set that equal to the charge on the plate, like technically the charge on the positive plate over 12 volts. And so the charge is whatever that times that is. Times 10 to the negative 6th. Someone's gonna tell me.
1.062 times 10 to the negative 10.
No, that.
Negative 6.
Pardon?
Negative 6.
1.062
2.
times
10 to the negative 6.
10 to the negative 6th. Okay.
Oh, okay, I see what I did wrong.
Okay.
I did negative 12.
Units?
Cool.
Yeah. So recognize, we are now in a situation here where I have this C and that C, and they mean two different things. This is for coulombs, comes right after the number. This is for capacitance. If I wanted to increase the charge on the plates, what can I change?
The voltage,
Do what with voltage?
you can change the voltage.
Which way would, if I want to increase the charge, which way would I change the voltage?
This one,
Louder, please.
the left.
To the left. I mean, do increase or decrease the voltage?
Increase. 'Cause
Yeah.
Yeah, increase.
Because capacitance is the amount of charge per voltage, so if I increase the voltage, I should get a greater charge. This ratio should stay the same. All right, so I can increase the voltage. What else could I do to increase the amount of charge on the plate? By the way, you can increase the voltage up to a certain point. There is a point at which, as you increase the voltage, you're gonna get more charge here, more charge here. The electrons hate each other. They're still trying to get away. If you crank it up to a high enough voltage, you will get a spark between the two. And that basically ruins the capacitor for practical reasons. So there is a maximum amount that's known as the dielectric strength. But we will not exceed that. However, there are some really nice videos out there where you have responsible people doing testing on that. And I'm sure there are irresponsible people also doing that. Also posting on YouTube. All right, so I can increase the voltage. What else could I do? Look at the math.
Does the distance between the plates affect the voltage?
Well, the distance between the plate affects the capacitance, and the capacitance affects the affects the charge. So what could you do to the distance?
Shorten it. Shorten
Okay. So if we shrink this, that would increase the capacitance. All right, so if we can get the plates closer together, that would do it. What else could we do?
it. Making plates bigger.
Say it again?
Making the area bigger.
Yes, and that's another thing that we could do. Now there is another thing, there's a fourth change that we could make, but we have to add something to this equation. If I stuck something in between the two plates, well, first off, it has to be an insulator. If I put a conductor between it, there's no capacitor there, charge would just flow right on through. All you need, if I have a buildup of charge here and here, if I just need to discharge it, I just need something to conduct it. In the case of a taser, human skin. So what I'm going to do is going to add an insulator, and in this context, known as a dielectric. This is an insulator. Typically, it's called a dielectric, at least where I've seen it, it's called a dielectric when it's as part of a capacitor. I don't think I really see dielectric as part of other things, otherwise it's just called an insulator. So I put something in between here. Because it's an insulator, I'm not going to get charges moving back and forth. What I am going to do is I'm going to start polarizing. So if we zoom in on this, if this is my positive and negative plate, I'm going to get these little polarizations throughout the dielectric. And each of these polarizations has its own electric field. So I'm going to end up with a bunch of little mini electric fields. It goes from positive to negative. So I have an overall, between the two plates, I have an electric field going this way. I add the dielectric, and I now have a lot of little electric fields going back the other way. So if the charge on the plates is fixed, we'll talk about how to fix that.